Good afternoon, everybody. This is our third edition of Beyond BIM, which originally started as a live event in London 3 years ago. Since then, clearly, we've had to go virtual, which has meant we've got less face-to-face interactions or connections. But nevertheless, we're able to draw on international speakers who may otherwise have been unable to join us live in London. Likewise, we have delegates from other European countries and the USA joining us. We aim to make this an event as a discussion forum, drawing in speakers and delegates who look to see where BIM can be extended into more than the 3D model, which some people see as the aim, but into the whole design and construction process, hence Beyond BIM. So one of our international speakers today is Abdulmajid Karanouh, who is joining us from UAE. He's got a slight problem with the sound, but we'll hopefully get him online by the time the presentation's over. Abdul has a background in mathematics, architecture, computation, engineering, construction, and research. Abdulmajid has developed over the past 20 years from a passionate specialist in high-tech architecture into an interdisciplinary strategist and design lead. As International Director and Head of Interdisciplinary Design and Innovation at Drees and Sommer, Abdulmajid's role and responsibilities include pushing the boundaries of innovation and technology through his interdisciplinary approach to design to assist clients in creating innovative project visions. Abdulmajid's journey involved working on many prestigious projects in collaboration with high-profile clients. One of his career highlights was leading the design-winning competition scheme for the Dhabi Towers and spearheading the design team to project completion in 2013. The project is winner of Best Innovation Award in 2012, offered by the Council for Tall Buildings and Urban Habitats. Listed in Times Magazine's Best 25 Inventions in 2012, and recently selected amongst the 50 most influential tall buildings of the last 50 years by the CTBUH. Abdulmajid is often hosted as keynote speaker at major conferences, academic and research institutes, while also contributing to major journals and publications on the subject of design innovation, the use of technology, including computation and BIM in the design and delivery of projects in the built environment. His presentation today, which is a recorded video, which we will play shortly, his title is An Interdisciplinary Approach to BIM Design and Communication. The multidisciplinary nature of the built environment creates many design coordination and communication challenges due to project stakeholders working in silos, varying in their mindset and approach to project delivery. Such challenges have a major impact on how BIM models are designed and communicated, bringing about a whole new set of challenges. This presentation offers an interdisciplinary approach to build synergies and related digital tools across various project stakeholders to address some of the main design and communication challenges faced in the application of BIM in a multidisciplinary environment. So Bev, if you'd like to run the video.
Thank you, Bev, and the rest of the DDE team for hosting me. And I would like to thank the audience for taking the time to watch this presentation. There are many major challenges that BIM application faces in a multidisciplinary environment, where various project stakeholders of various disciplines and backgrounds tend to work in silos, like issues related to ownership, scope, compatibility, interoperability, design criteria, and BIM criteria itself, among many others. When it comes to ownership, apart from the client, no single stakeholder owns everything, including BIM. For example, who owns the BIM model? At which stage does BIM start? which BIM software to use. How often is the same BIM platform used from feasibility to construction and operation stages? The analogy is like having a single vehicle that can be used as a sports car, a sedan, an SUV off-roader, a shipment truck, an excavator. Oh, and by the way, there's also autonomous and electric. Maybe one day, but we're not there yet, and neither is BIM. Lack of clarity in terms of ownership creates scope identification challenges, especially at the interfaces between different scopes owned by different stakeholders. Standard BIM may assist in resolving geometric coordination challenges. However, functional and operational coordination remains a major challenge. As different stakeholders think differently and use different tools to produce information in different formats, which create major data compatibility challenges. The larger and more complex the project, the more difficult it becomes to formulate a mental model or the bigger picture of the entire project in the minds of project stakeholders, a point that I will elaborate on later in the presentation. As different stakeholders operate differently, it creates many interoperability challenges, which is not just limited to software and file formats, but it also extends to how they strategize and process information, which has a direct impact on how they build and communicate their BIM models. The built environment industry is well established to a certain degree in terms of communicating the what and the end product, like the building geometry, material specs, and anything related to the project that is quantitatively measurable by nature. The industry, however, is far behind other industries in terms of capturing and communicating the why and the how, i.e. the design and construction and operation rationale, which may be qualitative and not as easily measured. The compartmentalized nature of how we think and operate in the built environment is clearly reflected in terms of how we construct and coordinate our BIM models, which often mirrors the challenges and problems explained earlier. Standard BIM models, for example, do not capture and communicate well the design rationale and its qualitative factors and drivers. Furthermore, as BIM models grow larger in complexity and size, they become too heavy and too confusing, like a maze, for standard users to manage and navigate through. A BIM model is therefore always at risk of becoming a black box that is only accessible to a few specialized operators with advanced technical skills and hardware. Therefore, a more dynamic, iterative, interdisciplinary model, as opposed to a standard multidisciplinary one, is suggested as first step to respond to this paradigm shift, where specialists from various disciplines and backgrounds are brought together under the umbrella of one team, from early feasibility stages and are maintained all the way through to construction and operation, so that the project knowledge and design rationale is neither lost nor distorted. The first case study that I'm going to present is the Dhabi Towers. In 2007, the Abu Dhabi Investment Council wanted their new headquarters to become a global landmark, inspired by the Abu Dhabi Vision 2030 that aspires for a state-of-the-art sustainable solution. The site sits opposite to trees and mangrove fields, facing north. We explore traditional local and regional architecture and how nature survives harsh weather conditions to inspire our concept, including beehives, cacti, and pineapples, where the latter is the nickname given to the towers by the locals. Regional heritage offers amazing lessons in terms of form and orientation, structure, courtyards, materiality, shading, and finally geometric composition, which is deeply rooted into the culture of the region, as we are about to explore. Former managing director at IDIS, Peter Orban, gave me a book which illustrates nicely how complex geometric patterns are constructed, primarily through intersecting circles and spheres. But what was the rationale that went behind them? In a nutshell, it is an implicit expression of unity with nature and the cosmos, using an abstract language that is universal, well-measured, and timeless. Mathematics and geometry fit that criteria very well. Circles and spheres were considered as the finite elements through which the smallest patterns to the largest building structures were constructed. We use the same principles to design an integrated solution. A cocoon-like form maximizes volume and minimizes surface area, which reduced energy exchange between the internal cooler environment and the external hotter one. The prominent spaces were oriented north as they receive less direct sunlight while also enjoying less views. Abu Dhabi is in a seismic zone, albeit not as critical as Tokyo or Los Angeles. A fully braced system would be an overkill, while a common diagrid system would be inefficient. A stretched honeycomb structure offered a better balance between vertical and diagonal bracing members, the first of its kind used on tower structures. This enabled us to integrate sky gardens on the south side of the building, and therefore reducing solar gain, while at the same time providing amenity spaces for occupants where they can enjoy some fresh air. The client wanted a high-tech building, but we needed to make sure that we have a solution that embraces the environment as opposed to defying it. A fine beige texture, for example, camouflages well dust and sand particles in the region over there. Now the elephant in the room, the shading screen. It was inspired by the Mashrabiyah, a traditional lattice screen popular in the region. The dense pattern shades the building very effectively, irrespective of orientation, while still allowing visibility and ventilation. The only downside to such screens is that they are fixed, which obstruct the view and admission of lighting when shading against direct sunlight is not required. We therefore infused the fourth dimension by developing an origami-like umbrella system that folds and unfolds with the movement of the sun. Yes, of course, we knew that the Institute of Mandahab gave up on making their dynamic facade work, but we thought that we may have an opportunity to take this beautiful concept to the next level. The system was designed as a triangular unitized unit activated by a central screwjack actuator. The screen comprises of a fiberglass mesh supported by aluminium frames and a duplex stainless steel structure. We conducted a durability test to test the mechanism over the course of 30,000 cycles, which is equivalent to 75 years in operation. And another wind tunnel test was conducted at 240 kilometers per hour wind speed to test its structural integrity. It passed both. Lightweight maintenance is done through air-sailing, while heavy-duty maintenance is done through BME units located at the top of the towers. The system is controlled by installed software informed by wind, water, and light sensors, especially to deal with unusual conditions. As no standards cover such design, a 400 pages Lego-like manual was developed to visually communicate the algorithmic principles of the building that enabled recreating the design using any software. More than 13 were used in total. I shall elaborate on the design communication later in the presentation, where BIM was critical to the process. The Mashrabiyah helps in cooling the building and in optimizing admission of natural light, while still providing use to the outside. It offers a unique experience and a great source of entertainment for occupants and visitors alike. The building is continuously used as a case study and referenced by various stakeholders across the built environment. What you're about to see was completely unplanned for, and it even took me by surprise when it happened. The government is using the building to celebrate their Independence Day every year. The Dhabi Towers won Best Innovation Award for year 2012, offered by the Council for Tall Building and Urban Habitat in Chicago, and has recently been listed among the 50 most influential towers over the past 50 years by the same body. It has become both a landmark and benchmark for context-considerate interdisciplinary design for generations to come. So that was a brief introduction to the project, but as promised earlier, it is important to elaborate on the project. It is important to elaborate on the design communication aspect, where BIM played a critical role in that. As the lead designer on the project, it became obvious early on that it would be nearly impossible, to limit the process to a single BIM software for the following reasons. The design complexity of the project is not limited to the building geometry, but it also extends to cover the building performance, especially the dynamic mechanism and its adaptive behavior of the Mashrabiyah screen. To overcome the challenge of design communication, we drew inspiration from the human DNA and logo manuals, where the former is a set of instructions that describe both the quantitative and the qualitative nature of the human body, how it grows and how it behaves, while the latter, Lego manual that is to say, offers a great example of how to communicate design using a human cognitive visual language that anyone from any background can understand and follow. A special mechanism to process the information and communicate in a diagrammatic visual fashion was developed to formulate a 400 pages set of visual instructions to construct and operate the building and its dynamic shading screen. I later developed the mechanism personally as part of my PhD research at the University of Bath, and I called it the design narrative algorithm, which communicates the design algorithm of any project in a visual diagrammatic fashion. A set of design development and interfacing rules were developed that also describe what the point cloud and the wireframes represent: finishes, structure, envelope, building services, etc. This lays the ground rules for scope ownership and scope interfacing as the design develops and evolves from stage to stage. These slides, for example, are part of the instructions that explain how the physical geometry of the design is constructed. These slides, on the other hand, are part of the instructions that explain the performance and behavior of the dynamic Mashrabiyah screen following the movement of the sun. The DNA enables us to use a scripting and software-free universal visual language that anybody can understand and use to generate their own scope using any digital tool or software of their choice. The DNA was issued to project stakeholders distributed in various geographic locations, from the US to Japan. Project stakeholders would each build their own model using any software of choice. The design team, for example, used Rhino, AutoCAD, Revit, Digital Project, 3ds Max, to name a few. The steel structure contractor, for instance, used Tekla, while the facade contractor used Inventor. In total, more than 13 different packages that I am aware of were used to develop the various scopes and elements of the building. All models are then assembled in Digital Project, which is more like an architectural version of CATIA, on-site in Abu Dhabi via Gary Technologies, who were our BIM consultants at the time. I think they're currently called Trimble. This is an image of the detailed master BIM model created in Digital Project, which is a combination of various models produced in various software. By the way, parts of this model was also produced in Digital Project. Highly detailed simulations and fabrication models were later produced to fabricate the first Mashrabiyah prototypes for physical testing. The following images describe the construction process outline. Here, for example, the architects produced the wireframe models, and then we passed it on to the engineers, who in return, and the specialist contractors, who in return produced their solid models. And finally, components are fabricated also using CNC machines, and laser-guided topographic machines were used for installation on site. This image of the building, this is an image of the building while the structure was being constructed. And this is an image of the building a year later after it was cladded. Following the DNA manual, 0 clashes were reported between the main supporting structure and the building envelope of the towers, which obviously are the highest in terms of complexity from a geometric and from a functional standpoint. Some internal shots, these are some internal shots showing the good level of shade that the Mashrabiyah provides, while still providing good levels of natural diffused light and good views to the outside. Some external shots showing how the Mashrabiyah shrouds the building, and a series of images on the right show the various folding positions and configurations of the dynamic unit throughout the day as they follow the movement of the sun. The entire design to construction process is summarized in this diagram, where it all started with the origami paper model. Then the design underwent a series of digital exploration, simulations, and analysis, from which the DNA manual was produced, which freed the process from being locked down to a single BIM software, to prototyping and mass fabrication, to mass installation and operation. Taking the concept of visual design communication to the next level to augment BIM, we have applied similar theories on a large confidential master plan, where this time we have included other design elements or other design factors that drive the design, including capital and operational costs. After having established the design criteria of the project, we developed a project data workflow to enable us to process any data in any format coming from any stakeholder and convert it into a format which we can integrate it into the master interdisciplinary design model. The analogy is like converting the input of all stakeholders into jigsaw pieces that can be assembled to communicate the bigger picture of all stakeholders and be able to update the bigger picture as the project develops, especially for high-level stakeholders like the client. A special data visual communication platform was developed to maintain an accurate mental model of the bigger picture of the entire project. The interdisciplinary design model of IDM comprises of a high-level round grasshopper representation of the master plan design, various technical and financial models in Excel, and Power BI to link all the models together parametrically in a user interface. The drop-down menu offers access to all kinds of project information like area, capital costs, operational costs, water and energy demand and consumption, waste management, mobility, and carbon footprint on emissions. This slide, for example, is showing the capital cost distribution across all master plan assets, and of course, every asset can be chosen separately and in isolation on the others. Here is a recorded video of the interactive nature of the user interface, where the user can zoom in and zoom out, spin the model around for more clarity while viewing the related information. For example, during one of the design reviews, some of the engineers were looking at the road, they were looking at the figures, and then they were looking at the actual geometry and topography of the road. They were able to discover some mismatches between the two. And this is the power of being able to link digital and text-based information with the visual side of the design, because then people will be able to relate in terms of what's going on and whether or not the figures make sense or match the image. Here, for example, it's clicking on the roads and it's showing the section and the road design and all information related to the roads. And we can do the same with building structures, for example, and other assets. So to summarize the presentation, we need to make sure that the design criteria, including the design development and interfacing rules, are well defined, because then this will pave the way to make sure that the BIM criteria in return reflects well the design criteria and its established rules. We should try to avoid as much as possible to lock down the process to a single BIM software. This is especially the case when we work on large, complex, and innovative projects. Always be flexible to use the right tool for the right stakeholder and discipline at the right project stage. Maximize the use of visual techniques to capture and communicate design and its rationale using a cognitive-friendly language that anyone can understand. Thank you very much for your attention.